Okay, so starting recording. So I'm going to start with this first set of notes here. So hopefully y'all can see the notes as I'm presenting them here. So yeah, I'm going to go through the first set of notes. Then I'll stop that recording though and go through the second set of notes. And hopefully it will make some sense. So hopefully y'all have at least looked over these notes before you got to class. Hopefully you've looked at some reading. That should help you. Okay, so we're talking about electric potential and electric potential energy. So we had the test at the end of last week. Some of you actually did it, which is cool, I guess. This week we're starting our study of electric potential and electric potential energy. And so they're very similar to electric field and electric force. The main difference is that they're not vectors, and as you'll see today, that changes things a little bit. I think it makes things simpler, but you gotta think about it. So let's go ahead and jump in here. So to start off with, we talked about the conservation of energy, which you guys should hopefully know. So again, conservation of energy, if you don't remember, is just saying that in a closed system, your energy is conserved. So again, if the system is closed, no energy enters or leaves the system. So, can't see my screen. Okay, well let's try that again. You should be seeing my screen. Let's see here. No, you can't see my screen. No. Alright, now can you see my screen? Yeah, I think you should be able to see it now. So this was the previous screen. Alright. Yeah, I forgot I turned that off for a second. So, as I was saying, energy is conserved in a closed system, which means that you're not losing any energy to friction or anything like that. So when we're looking at this, we're starting off with conservation of energy. We're saying, okay, if we're assuming, there's no friction, a nice, ideal, perfect system, let's think about something like a spring. Okay, and as you can see from the picture here, you have a spring. In this case, it's just pushed against the wall. We're not thinking about gravity or anything like that. So as you take this spring and you compress it with your hand, you apply a force over a distance. You do work. Okay. Now, there's the work energy theorem that says work is equal to your change in kinetic energy, but the spring isn't moving. So in this case, your work is going to be equal to your change in potential energy, specifically the energy contained in the spring, which theoretically you learned last year how to calculate all of those things. We're not really going back to that, but it's just keep those thoughts in mind. So if you think about that, you can do basically the same thing with electric charges. So in this case, it gives you a picture of a bunch of positive charges, and those are considered the source charges. So think about those as just being permanently fixed, in place, like they're not going to move. It's kind of like our wall. And then we're taking a second or a different charge, and we're going to push it with our hand towards our source charges. Since they're all the same charge, they're going to repel, and so you're going to have to apply a force over the distance over which you move it, and you will still do work. Well, this will also have a potential energy stored in it, just like the spring. And just like the spring, if you let go of your hand on the spring, it will start to, uncoil or spring, if you will. And the electric charge would do the same thing. If you move your hand, it will go shooting off in the other direction. So in this case, you can see there's a similarity here, that the work you did is equal to a change in your potential energy. Now, I'm not going to get too much into the signs right now, but I do want to mention that work should equal the change in your kinetic energy. So when we're talking about potential energy, it would be equal to the negative change in your potential. And so basically, your delta ends up being backwards, but we'll get to that a little later. But hopefully this makes sense. You you do work, you apply force over distance, and you have stored energy into the system. Okay, so here you can see that we can calculate the electric potential energy as based on this formula here. U equals K Q1 Q2 over the distance squared. K being 1 over 4 pi epsilon naught, or that's the electrical constant, nothing changes there. And then we have, our two charges, Q1, Q2 over D. Now notice this is very, very similar to our force formula. Remember, force was basically the same thing, but over D squared. That's literally the only difference. That energy is just over D, whereas force is over D squared. Well, I should say that's the only difference in the formula. The other difference is this is not a vector. So there's no direction to this. You can have positive and negative energies, as we'll see here, but they don't have a direction to them, which can be a little confusing. So there's no vector, so the math is super, super easy, as you'll see. But the conceptual part is a little bit harder for this. So it says in the case where Q and Q prime, just think of them as Q1, Q2, are opposite charges, the potential energy of the charges is negative, and it would be the opposite if they were, positive. So here it shows you a graph, and you can think of it like, okay, if I have the stationary positive charge, but I'm moving a negative charge towards it, well, it's going to want to get closer rather than farther. So you don't actually have to do work to push them closer. You have to do work to get them further apart. And so the energy ends up being the opposite of what we had before. It's calculated the exact same way. And so as a result, we say it has a negative potential energy as it gets closer because it's going to want to keep falling closer. So to do positive, energy, or to do work, you'd have to go the opposite direction. So when it comes to mathematically calculating this stuff, with vectors, that formula you had was only for the magnitude. Like, the formula calculated the magnitude, then you had to use your brain to think about the direction. Here, you just plug literally everything into the formula. You plug positives as positive, negative charges as negative, and your potential energy will come out positive or negative. Obviously, if it's a positive and negative, it will come out with a negative potential. Two positives or two negatives will come out with a positive potential. And essentially, you can think of them as, attracting or repelling. But it's based on the energy, because what's going to happen here is that, like, if you have like a negative potential, that means that if you leave everything like that, things are going to end up speeding up because they're getting closer together. And if they're positive, they'll end up speeding up because they're going to get further apart. So yeah, it'll make more sense as we go through some more of this here. So here it says question 1, what is the electric potential energy stored in a 2 nanocoulomb charge that it's 1 centimeter from a second 1 nanocoulomb charge? Okay, well, I just gave you the formula for this, so you just plug in. You go K Q1 Q2 over the distance squared, so make sure you convert that all to coulombs and meters, and you should get 2 times 10 to the negative 6 if I did this correctly. But again, I may have said this incorrectly. The distance is not squared, so obviously. So you just plug that in, you should get that number. Make sure to try that out on your own, just for a little practice. But then it says, what would the electric potential be if the 2 nanocoulomb charge was negative? Well, you just plug in a negative, and it comes out to a negative potential energy. Negative potential energies aren't something that we studied too much when it came to like gravity or springs in terms of their potential energy, because they don't really make any sense. Negative potential energies make sense in the terms of things are going to get more negative the more negative you get. Like, they're going to go, like, think about something rolling downhill. Like, if you think about a gravitational equivalent, if you think about sea level as being 0, and you have something on the top of a hill and it starts to roll down, you go, okay, well, it's going to get kinetic energy. Well, that would be true until you hit sea level. But if the hill was big enough that, it say went below sea level, well, then you would have a negative potential energy. And that just means that it's just going to keep going down until something stops it. So it's kind of the same thing here, that it's going to go down and go down faster. So U is electric potential energy. That is what U means. So U is our standard symbol for potential energy. So anytime you see U, it's potential energy. So specifically, U with a little E on it would be electric potential energy. So it says, to better understand electric potential energy, we take a charge at 10 nanocoulombs and set U0 equals 0 at point A. This is kind of similar to setting ground level to being 0 with gravity. It's arbitrary. We could pick any point to be 0, and typically we pick, sea level to be 0, but again, you can go below that. So typically what we try to do is we try to say, if you're infinitely far away, that distance would be infinite, and so U would be 0 at that point. So you go, okay, you're infinitely far away, that's 0, so now as we bring it closer, what's the energy? So something kind of like that. So at point A, it says the potential energy is 0. What's potential energy at point B or C? Well, to figure out that energy, we simply just figure out the amount of work to move it to point B or C. So it takes 4, for this example here, it says it takes 4 microjoules of work to move the charge to point B. Or it takes 6 microjoules of work to move it to point C. So this is just given to us. It's not giving us any numbers for this. So we're just kind of taking this picture at face value here. So think about that. Just think, okay, I got this charge and I measure the force I'm applying and I measure the distance over it with, and I got 4 joules to move it to point B, 6 microjoules to move it to point C. Okay? That is the potential energy at those particular points. Okay? And so obviously the potential energy depends on the point you're looking at. And if I didn't mention this earlier, it's potential energy, so energy in the metric system is measured in joules. So here this says, okay, if we took a charge that had 20 nanocoulombs, then according to Coulomb's law, the force on the charge would be twice that with a 10 nanocoulomb charge. So what it's saying is, for the previous situation, if you had a 10 nanocoulomb charge to start with, well, then you'd have to use a 20 nanocoulomb charge now. What's the difference? Well, according to Coulomb's law, you'd have to do twice as much work for twice the charge. That makes sense. So the charge's potential energy, its electric potential energy, as we see, is directly proportional to its charge. So it depends, A, on the source charges, but B, also on the charge that you're physically moving. Just like with gravitational potential energy. Like, gravitational potential energy in the simple form is mgh. That m is the mass of the object, and so the energy gravitationally is the same, or it's dependent on the mass of the object, just like the electric potential energy is dependent on the charge. So this says a bunch of stuff. It says, the electric potential energy is 10 nanocoulombs for 4 microjoules at this given point. Then at the same point, the potential energy is 8 microjoules for a 20 nanocoulomb charge, and would be only 2 microjoules for a 5 nanocoulomb charge. So it turns out that if we're looking at just moving it from point A to, say, point B in our previous example here, so if we go back, just think about moving a charge from here to there. Okay, just ignore C for the time being. So let's say that this was 10 nanocoulombs and I moved here. Okay, well, it required 4 microjoules of work. So now I go to 20 nanocoulombs. Okay, now it requires 8. Or 5 microcoulombs. Now it is 5 is like 2 microjoules of work. So what it's trying to say here is you can see that the potential energy is directly dependent on how much charge I'm moving. Well, if I take the amount of work I did, that potential energy at that point, and I divide it by the charge that I put at that point, I get a constant ratio. Okay, so in this case, 400 joules per coulomb. It's not going to be the same every time, but it's the same at this point for this particular set of charges. It turns out that that 400 joules per coulomb is much more useful than finding the electric potential energy of a particular charge. Now, you might want to find the electric potential energy for a particular charge, but it's not as useful as this ratio that we've now kind of discovered. And so you can kind of think of this like thinking about gravitational potential energy. Think about if I take a mass, mgh, and I put that mass at a certain height above the ground, it will have a certain gravitational potential energy. But you guys know that regardless of what mass I put at this point, so let's say we're looking 20 feet above the ground, no matter what mass I put there, okay, that's going to have some potential energy. How much potential energy? Well, it kind of depends on what mass you put there, but you physically know that something being at that spot, 20 feet above the ground, is going to have some energy to it, right? And for most objects, you probably don't want it to fall on your head just because it's 20 feet above the ground, regardless of the actual mass. And so that's what we're doing here, is you can kind of think of like we cut out the mass and we're just looking at GH. G, little g, is dependent on the Earth, the size of the Earth, and H is just the distance you're above the Earth. And so that's kind of what we're looking at here, that this 400 joules per coulomb is just based on, well, the source charges and has nothing to do with the charge that you're putting there. And so if we do this, this gives us units of joules per coulomb, okay? And so this gives us a little formula here that we can have the express for electric potential energy that any charge would have if placed at that same point is essentially that, U, electric potential energy, is this quantity times our charge. And this quantity has a very specific name. Its specific name is called electric potential. So I'll say that again. This 400 joules per coulomb has a specific name. It's not always 400 joules per coulomb, but its specific name is electric potential. So we have electric potential energy, which is U. We have this guy whose symbol is a V, is electric potential. Electric potential, its units are joules per coulomb, but they're also known as volts. More commonly, electric potential is known as voltage. Okay? So, well, before we get to that question, I want to make sure you guys understand this. So, you guys have heard of voltage a lot. You can say voltage, and like I said, a lot of people say voltage. I say voltage, it's fine. But the actual name of voltage is electric potential. And so you guys got to know that, like when I ask you questions and stuff, I'm going to say electric potential, I'll say electric potential energy, I'll say voltage. But electric potential energy is not the same as the other two. Electric potential energy is U. Electric potential, its symbol is V, and its unit is V, voltage. But voltage, or volt, like 1 volt, is equal to 1 joule per coulomb. Okay, as we'll kind of define here in the notes. That is electric potential. So electric potential is essentially finding like the potential energy of a particular charge at this point and then just dividing by whatever charge you put there and finding the voltage. So voltage is much more commonly used than electric potential energy, just like the electric field is much more commonly used than electric force because, well, it's easier to express it without the source or without your particular thing being at that point. So let's look at this question here. It says, as a positive charge is moved from position I to position F, its change is its change in electric potential energy, so U, positive, negative, or zero. So for example here we're looking at point I. So we're going to move a positive charge from I to F. So it doesn't matter how you get here, you can go like around like this or whatever. So here, if you're thinking about your potential energy, you're thinking about that formula K, Q1, Q2 over the distance. So here in this case, it's the same charge. There's no charge difference, right? Q1 and Q2 are the same. And the distance is the same. So there is no charge going from the initial to the final position. There's no difference in the electric potential energy. So I'd say 0 for the first one. Then the second one, it says IF. So here we're moving from here to there. So charges don't change, but the distance increases. So I would say that's a decrease in potential energy. It's change in electric potential energy, so it should be decreased. So B should be our answer. And we'll go through the others, just to be safe. So you go from I to F. Now this one's a little confusing on 3 because you go, okay, well the distance increased. If they were both positive charges, then that would contribute to a decrease in the potential energy. But since one is negative, or remember our test charge is positive, it's going to get more, how do I say this? You're going to divide so the overall number gets smaller, but it's still negative. So a smaller negative would be closer to positive. Think about that. Possibly put some numbers into it and prove it to yourself. And then 4, you're going from I to F. So here, obviously, you're closer and get further away at point F. Yes, you're getting further away from both charges, so it's going to decrease. So I'd say the only one here that you're going to have to really think about is 3. So make sure you think about that and prove that to yourself. It's kind of like a double negative almost. Okay, so we talked about electric potential energy and kind of where electric potential comes from. The definition of electric potential is the electric potential energy divided by the charge at your particular point. And so this is the definition of voltage. But you can also calculate it as KQ1 over the distance squared. So again, it's those source charges divided by whatever distance you're looking at. But K is still in there, or 4 pi epsilon naught, however you want to say it. So this tells us how a source charge will exert force on a charge that you place at this point. Okay. And as it says right here, 1 volt is 1 joule per coulomb. So again, typically we call potential energy electric potential. Voltage because of its unit volts, but that's the same as calling, like, say, electric current amperage. Sounds weirder, but some people say it. So, but again, voltage is a pretty common name. But remember, voltage is electric potential. That is the number one thing you need to learn today, besides these formulas. That's the same thing. Okay, so this brings us to a little thing called EMF. So when batteries are considered, sometimes the voltage provided by the battery is called EMF, or EMF stands for electromotive force. So sometimes when you're looking at a circuit, I know we're not to circuits yet, and we won't get there today, but when you're thinking about circuits, you go, okay, well, sometimes you see the voltage source. Sometimes they'll just say voltage 10 volts or whatever. But sometimes you'll see it listed as a battery, say the EMF is 6 volts. So what the heck is going on there? So here this is kind of like a sidebar to explain what EMF is. So EMF of a battery is the voltage produced by a chemical reaction in ideal conditions. So most batteries, there's some sort of chemical reaction. Even rechargeable batteries still rely on some bit of chemistry to occur. As a result, it turns out that the chemical reactions are under nice, perfect conditions, but for most batteries, the actual output will be less than ideal conditions because we don't live in a perfect world. So electromotive force, if something says EMF, they're talking about the battery in perfect, you know, essentially non-real world conditions. And then if they're saying like the output, you know, they say the terminal voltage of the battery, that's what the battery is actually putting out. And it says right here, we're going to learn how to account for that in the next unit, and we will. But essentially, the reason why you guys have to learn this is because, you know, there's a lot of things that we do in physics. It's like, well, this is, you know, perfect world, and then we'll look at reality. Well, this is one of those times where you really have to understand the perfect world to have any semblance to grip what's going on in reality. Because if you think about just a regular battery, you know, just think about just a regular AA, you know, it's not rechargeable or any of that nonsense yet. Just a regular AA battery. It's a chemical reaction. And what happens to these batteries is, you guys know this. If you have just a regular battery, even if you don't use it, if you just let it sit on the shelf, if you let it sit long enough, that battery will just completely corrode and dissolve. Because it turns out there are chemicals, you know, acids, in these batteries, and the reaction that's occurring, you know, occurs fastest when the battery is actually connected to a circuit, but will still occur even when it's not connected. And because of that, what ends up happening is when it's not connected, it actually eats away at the internal components of the battery, thus lowering the actual voltage output of the battery. And so an actual battery, when, like if you test a battery by itself, that will essentially give you the EMF. But then if you connect that same battery to a circuit and test the voltage while it's powering something, that will give you the terminal voltage. That may not make a whole lot of sense right now, but we're going to do a whole lab on this. Because it is that important. Because what happens is, in reality, if you have a battery, let's say you buy a brand new AA at the store and you test that voltage, it'll say it puts out like 1.6 volts. But on the package it says it only puts out 1.5. And you're like, what's going on here? Well, the 1.6 would be the EMF, and the 1.5 is the terminal voltage. But as that battery gets older and older, even if you're not using it, you know, a year later down the road, it's probably only putting out 1.4 volts. Okay, was that battery still good? It kind of depends on the circuit you're using. And so the EMF is what it puts out in ideal conditions, and that's like what your battery tester would measure. But then you're like, okay, this battery should work, and then you go put it in circuit and it doesn't work. Well, what's going on here? Well, it's the difference because of what the battery can theoretically put out and what it can actually put out because of the actual chemistry, which is something I thought you guys would learn in chemistry, and I have been proven wrong. So that's why we're going to take a little time at the beginning of our next unit to dive into batteries a little bit more detail. Because yes, it's definitely a chemistry thing, but you know, as I've just mentioned here, there's quite a bit going on, and I feel like if you guys kind of get in there a little bit, it'll make more sense. But we're going to wait for that until we actually start circuits. Okay. Where's my slide? Well, okay. That was weird. So, question 3, it says, what's the electric potential 1 centimeter from a 1 nanocoulomb charge? So you just plug it into that voltage formula, K, Q over the distance. Again, using correct units, you should get about 900 volts, which is a significantly high voltage. And this point brings up the fact that voltage, just because it's high doesn't mean it's going to kill you. It's not the height of the cliff that kills you, it's how quickly you get down from the cliff. Right? So just think about that. So 10,000 volts, for instance, when I hooked students up to the Van de Graaff, that was at least 3,000 volts I had y'all touching. Y'all were fine. B, it says, what's the potential difference between a 0.1 centimeter away and a second point 3 centimeters away? So you're comparing this point with another point that's 3 centimeters away. So to find that potential difference, well, you just calculate it a second time and then subtract the two. Final minus initial. So it could be 600 volts or negative 600, depending on which one you call final or initial. And this is essentially how a battery works. That batteries have charges in them, and they have different voltages. One at the positive end and one at the negative end. And to get that, 1.5 volt difference is simply the delta V between the two ends. And so one of the things you guys should know is that if you just take a battery and turn it around backwards, well, now you get the voltage negative, which is generally not something you want to do with your voltages, which is why they tell you to put the battery in one particular way. So a lot of times in this class, we can calculate voltages, and we're certainly going to use this formula, but more often than not, we're going to find a delta V, a potential difference, because again, that's going to be more useful in, say, a circuit. Here, this gives us question 4. It says 2 charges are each brought separately into the vicinity of a fixed charge, positive Q. The first is a positive Q brought to point A, which is a distance r away. The second one, then it's removed. Then you bring a second charge in, which is the same size but negative. It's now brought to point A. So the electric potential, this is voltage, right? V, is what? Greater for one, greater for two, same for both. Well, just looking at the formula, the answer should be kind of obvious that it's the same for both. It's not, having gone through that potential energy thing, you're like, well, I got to put the negatives in there. That's true. You should put negatives in there, but it's only for the source charge. Source charge didn't change. It absolutely matters nothing of what you put at that point, because we're talking about the voltage. Now, the potential energy would be vastly different for these two charges, but voltage is the same. Okay, because to get from voltage to potential energy, you would multiply by your charge. So, one would have a positive, if you're talking about the energy, one would have a positive energy, one would have a negative energy, but the voltage is exactly the same because it depends on the source charge, which didn't change. And I guess we're waiting on this again. How many more slides does this thing have? Oh my, okay. What is going on here? Question 4. Okay. Well, this is a little frustrating. Why is it not loading? Well, don't know why it's not loading that. If I remember this picture correctly, I'm not going to bother with the analysis of the last question here. Sure, it's taking its sweet time. But when it comes to this picture that should be loading here, which is not, let's exit this. So it says typical voltages. It should just be a picture, which is right here. I know it's right here. Of just typical voltages, as it says. So, it's just voltage of common things. Well, it's not just batteries, but it's, y'all can probably see it. I don't know why my internet's being weird. Actually, I know exactly why my internet's being weird, and it's my own fault. So this is just typical voltages that you find. So I know you're not able to see it here. So look on the actual set of notes, look over these. And then here, this question, as it says here, question 5, which is also deciding not to load. This is the, what do you call it? It's a free response question, and it goes through, E parts. And if I remember correctly, this is the this is a really good analysis question. But it has all the answers and stuff there. So if you want to take a look at it. Okay, well, thank you, Peyton. Yeah, so it gives us different energy potentials, of like a brain and a battery and household electricity, just to give you guys some ideas of typical voltages. Because I said that AA battery is 1.5 volts. I find a lot of people don't know that, which is weird because it's written on the side of the battery. But by law, the voltage is written on the side of the battery. So if you have a battery, it should say that on there. So yeah, this question 5 is just a good analysis question, and to me it's a real good demonstration of the difference between voltage, potential energy, but also electric force and electric field. This is one of those questions where I can run through it. It's not going to really help you guys that much. What's really going to help you guys is to sit down and try to work this on your own. Just take it at face value and go, okay, it's asking me to do this. Try to calculate it. Then come back and look at these answers and figure out, okay, I did that right, or oh gosh, I did that really wrong. And what you'll see is that the vector stuff is a pain in the butt, as you guys already know. But the electric potential energy and electric potential stuff is really easy, but also super easy to get wrong. So just take your time, kind of work through it. We're not going to do that today for a couple of reasons. Number one, it didn't load, but also number two, I want to make sure to finish recording this. So I'm going to stop this recording here.